It's my great pleasure to introduce the next speaker, Dr. Stu Solet from ExxonMobil Research and Engineering. Dr. Solet has over 80 U.S. patents. Last year, he was the recipient of the Hermes Pine Award in Catalysis and is on the editorial board of the Journal of Catalysis. He has many other awards to his name, including the coveted Frank Ciapata Lectureships, the ACS Innovation Award, ACS Heroes in Chemistry Award, and the title of his presentation is Learnings from Cobalt Fischer Tropsch Catalyst Studies. Thank you very much.
Thank you very much. Excuse me. Very happy to be here today, and Burt, I'm glad we had time last night, so we have some time for the talk today, and not just to roast you. So I'm going to tell you about some of the things we learned during the course of several cycles of Fischer Tropsch synthesis studies at ExxonMobil. You're going to see a slight contrast from the previous talk. We came to a slightly different conclusion, sort of totally different, but so this should be fun. Okay, so basically what I'm going to try to review, and sort of the heart of my topic, revolves around this issue of deactivation. And I'm going to go over some of the reversible and irreversible pathways that at least we thought we found in our studies. And the sort of underlying theme of the catalytic theme is cobalt particle uniformity and how that plays a very critical role. So we're going to talk about how that happens, and then some newer material that we've included in this talk that we haven't talked about much before, approaches to create more uniform distributions. Since the question that we had at the last talk was, if you have some idea about what's creating the deactivation, what are you going to do to try to ameliorate it to some degree? So hopefully I can get into most of this. Okay, so of course we were interested in syngas derived from natural gas. And when you look at the stoichiometry that you have here, one of the things that you see in spades is water. Now, I normally like water. I drink it all the time. It's one of my favorite beverages. But water is not always the most favorite thing for Fischer Tropsch chemistry, and in several aspects. One, just initially, it limits the overall thermal efficiency of the whole process, which is rather unfortunate, right? Because every time we make a CH2, we get some H2O. So 2 hydrogens in a carbon are good, you can use it for fuel. Water is already burned. So that, in essence, is a part of the penalty we pay for activating the methane. Okay, so, but there's another consequence, and that's on catalyst performance. And we're going to see that in several aspects here. We think that, at least in our feeling, most of the deactivation that we observe can ultimately be related to the presence of water. So we're going to talk about 3 different pathways, one involving cobalt surface oxidation, and this is a reversible one, and that is in the presence of water in the reactor. You can get some oxidation of the surface, and therefore once it goes to the oxide and not cobalt metal. You can also, over time, develop a mixed metal oxide. It can be, depending on what your support is, cobalt aluminate, cobalt silicate, cobalt titanate, surface forms of these mixed metal oxides that become irreducible under FT conditions. And the third part, which is we really saw and studied a lot in detail, is the effect of cobalt agglomeration. So let me start going over some of this. So the evidence for the reversible cobalt oxidation, that comes out pretty clear when you start doing reaction studies. And we also have some microscopy to sort of show exactly what's happening. So here is a Fischer Tropsch catalyst after it's gone through some cycles, and it's after running the conversion. Normally these conversions are 60% or so. And normally you'll see some slow deactivation with time. And here's a particular region of the catalyst. And what we did, and what our microscopist, Chris Cleaver, has been able to do, is to take these samples out, treat them in either hydrogen or in a little mini Fischer Tropsch reactor, and put them back into the microscope in the same exact spot after they've undergone this treatment. So what we do is, we know what in a little mini reactor, we know what space velocity we have. We put the little carbon holder that has the catalyst on it at the exit of the reactor, so that it's seeing conditions and conversions that we would see in our normal reactor. And we can run that for varying periods of time and then put it back into the microscope and get back to the same exact spot that we had before. And that really helps. So what we do here, going from A to B, is a hydrogen treatment, and that's often done. You just turn off the syngas and put in hydrogen and the temperature reaction, 200, 220C. And now you see the same region. Now a lot of these small particles of cobalt show up, and not here, because you don't have the contrast when you form the oxide here. And when you do that, you see the activity go up. Now that activity is somewhat transitory and does tend to come back down to a steady state behavior, but you do see these particles, and then you run it for some more time, see, and you start to lose the ability to see those particles. So you can do that over and over again, and it comes back mostly. So that's an effect of water, but not a bad effect in that it's reversible, mostly reversible. It will affect the smaller cobalt particles first, and although it is reversible, we think that in essence, over a long period of time, and a lot of the studies I'm going to talk to you about today have been for catalysts that have been run for months on stream, that things happen. You can get the two deactivation issues caused by this type of cycling and also by the presence of water over a long period of time. So let's go into that. The formation of irreducible mixed metal oxides. We have a very simple experiment. It's not as elegant as what we learned in prior talk, but we think if you have a very good piece of TG equipment, and we do, you can do something very, very informative here. So we take the catalyst after it's been in our unit, and most of the studies we've been talking about today have been in a bubble column unit. We take it out, we clean the wax off, and then we go ahead and we treat that. So we start with the catalyst then that's been in the unit, taken out, the wax has been extracted, it's in some arbitrary redox state. We don't know where it is, it's been exposed to the air. But then we do a reduction, and we do that reduction at 375C. Now that's pretty high reduction, and in addition to being fairly high temperature, there are noble metal promoters in this catalyst, and some of them are very good hydrogenolysis components and used in hydrogenolysis catalysts. So what happens when you get to this reduction at 375, basically two things can happen. You can reduce the cobalt down to cobalt metal, and you're going to get some sort of weight loss on your TG. It's going to be meaningless, though, because this point here is arbitrary. Or you can lock it in and get some cobalt plus 2. That just doesn't reduce because you have some stabilized mixed metal oxides. Now you go ahead and you do an oxidation. You take that up in air up to 500 degrees C. This weight loss, this weight gain, you can measure very exactly, and it is very meaningful. Then you go on and you reduce it again, and again it can come down to here, or it can come all the way down to here, and you measure a second time. Now when you do both of these and you compare this O1 and O2, you get information out of that too, and some of that information is, well, what is the total amount of the oxidation that went on? From that you can figure out what's the total amount of cobalt that's there that's been oxidized, so you can get a guess between whether it's, or get an estimate I should say, between cobalt 0 and cobalt 2. But also, if you don't have a large difference between these two, then if there was some carbon left, if you thought that this was not enough hydrogenolysis activity to get your carbon off the species, you're going to get a difference in value because you're going to get a weight loss from the oxidation from having that extra carbon on there. Generally speaking, in essentially every case we ever tested, we either got exact values for O1 and O2 or within 1/100%. So we didn't feel that there was any really appreciable carbon left on our catalyst after we did that treatment. Nonetheless, if you took these catalysts over here after they reduced to 375, you would often have significant deactivation that you could not recover. So again, part of the reason why we come to a different conclusion. Now, it could be that we just have different catalysts, and we do have a strong hydrogenolysis component on ours. So that's one. So we take that data, and then we figure out how much oxidized or cobalt that's not able to be reduced, how much stabilized, oxidized cobalt we have, and we plot that over time. So here are some data that we have of samples that were taken out during the course of a 6-month run. And we look at them after we reduce them at two different temperatures, 375 and 225. This is more or less the temperature in the reactor. This is the temperature, sort of the pre-reduction temperature. And you can see if you take the material out of the unit, you're getting a slow accumulation of irreducible oxides over the period of the 6 months. And you're losing about 9%, close to 10% of your cobalt manifold by forming these. If you're able to take it up higher, well, some of that you can recover by going to 375, but so there's intermediate states of this irreducible oxide. Some is a little more easy to reduce. You can actually see these differences with XPS measurements. But you do remain even at 375 with some that you can't reduce. So this is one means of losing some cobalt from your manifold that's not recoverable by hydrogen treatments. So this has gone from reversible to irreversible. This is not the major source that we found. The major source that we found has to do with the growth of the cobalt particles. And the first evidence we had of that was also a very simple experiment, and it's due to the observation that, when you oxidize cobalt, the rate at which you do that oxidation is dependent on the size of the cobalt. Not in a very quantitative way, but in a qualitative way, you can see it quite nicely. So if you take a reduced cobalt species and then you just heat it in air in a program mode, you will see a pattern that looks something like this. And this sample is taken out of a fresh catalyst. Now you have to take the sample, you have to passivate it first. So you reduce it, you passivate it, and then you do this oxidation step. Otherwise you can create a little bit of flames in your lab. Okay, so don't recommend that experiment. However, if you take a sample at the end of the run, then you get something that looks like this green curve. And now it's very different. I mean, this difference is not just a little bit, it's a lot. And you can see the fact that that cobalt is oxidizing at a slow rate. We don't have a quantitative way of relating this to size. We're going to use microscopy to do that. But this is a very quick and sort of dirty way of seeing that you have actually obtained larger cobalt crystallites at the end of the run. So this is a point after 180 days of essentially a good run. We've had other runs where other things have happened where you can get to this situation sometime sooner. So it's a concern. The other thing that you see, if you go ahead and do the second cycle, just like we did before to look at the cobalt, the mixed metal, the formation of the cobalt aluminates, titanates, and silicates, and you do a second cycle, interesting, you go ahead and you take this now, you reduce it, and then reoxidize it again. Now the peak has moved back a little bit. So isn't that odd? We said that the particles were larger, but then when we oxidize it, re-reduce it, it's fairly similar to the starting material. So we're going to come back to this point as we get a little further along. There is information in here, and you go, well, are you trying to tell me that the particles are getting smaller by going through that cycle? And the answer is yes, but it's yes, but, as we'll see later what the but is. Okay, so let's go on now and try to get to what the root of some of these issues are that we have to try to deal with. And that has to deal with the uniformity of the samples. We heard some of these yesterday from Brian. And we saw very clearly, and let me sort of tell you a little bit more about what these axes are, because it's various times we've had to sort of remove some numbers. So this is the 6-month run. So we're talking about the data over 6 months. We're talking about cobalt particle sizes of going from approximately 10 nanometers to approximately 15 or so nanometers. And this is a more uniform sample, and we call it the nanoscale homogeneity, reasonably good in this sample. We have one here, a second sample, where actually the particles are smaller, but they're very clustered. And so we start out with a higher activity, but you see two things happen. One, it's deactivation, the particles grow faster, and they also grow to a larger total size. So there's kind of a kinetic effect, and there's also a sort of a pseudo-equilibrated effect of the size that's determined by this. So the kinetics is normally determined by it's usually a function of 1 over r squared of the particle size, and therefore actually as the particles get bigger and then the space between them or the distance between them increases, the rate tends to slow down of their growth. And you will reach a pseudo-equilibrated size, which is a good thing, although of course you're losing activity during that whole process, so you'd like to avoid it. If they're really close together, they not only, when they're small, they grow faster, but they really come together. And we're going to see that in very, very much detail here. Again, some evidence that water plays a role here. If we look at the growth of the crystallites at the outlet of the reactor, and these are for 2 different catalysts and 2 different runs, we always have seen this, that this is done in a fixed bed, not in a back mixed slurry reactor. So if you do the same experiments in a fixed bed, where you have more water towards the exit, you do see more particle growth towards the exit of the reactor. So in the slurry reactor, where you have a lot of back mixing, that's some ways it's actually more problematic because now everything sees the concentration of the exit composition, and so your whole ensemble of cobalt sees a high water content if you're running at high conversions. So this can force you, if you have these issues, to run at lower conversions, but then you need more reactors, and so there's a lot of economics and engineering in this. But it's usually, or in our opinion, it's all tied to this homogeneous distribution and to this growth. We also have evidence here was a partially reduced catalyst. We actually started with some oxide, and we had very rapid particle growth in that one. So the question came up, what type of mechanism do we have in the growth? And there's generally two. One is coalescence, where particles essentially come together and grow. Let me emphasize that we're not talking about particles rolling on the surface, but particles being close to one another that come into contact. And we have one ripening where there's an atomic movement on the surface. And in the end, you wind up with the same situation, although what goes on in the middle can be quite different. Oftentimes in the ripening process, you do wind up with the movement of particles, of atoms, creating smaller particles and larger ones, and eventually the smaller ones wipe themselves out. But sometimes you can see this intermediate distribution. Okay, so what did we see? Here's some of what we saw. Again, this was work that Chris Cleaver had done for us, where she was able to take micrographs of the samples. She would run it in a little lab unit, take the holy carbon filament, run it at a given conversion, so it would see a certain amount of water. It wasn't in the microscope. There's no way you could do that. But run it for varying periods of time, up to several months, putting it back into the unit and getting back to the same particles at different times. So here's a start of run, and you can see in this particular view, there are some particles that are fairly close together. This is day 32, and now you can see the particles have come. Sometimes the pictures get just a little bit rotated relative to one another, but it's the same region. They've come together, and here you can actually see where they've, like two lovesick amoeba, they've come together and formed a given particle. And here at day 48, another 16 days, you can really see these three having come together, and here's the particle there. So that's one. Here's another view where the close ones come together over here by day 32, and by day 48, you can't even see the fact that there were two separate particles at one time. They've come together. So we've also never seen any of that intermediate state where we have smaller and larger. We only see larger. But again, I want to emphasize that we don't think that the particles are rolling around bumping into each other, but they start close to one another. Because of this oxidation, the oxidized species, be they oxides or hydroxides, tend to wet the surface more strongly. And that tends to spread them out. So if they're close together, they can form this aggregation, and that's essentially what I've tried to explain here. Now let's go back to what we were talking about before, this funny result that we saw when we looked at the oxidation kinetics. We saw the end of run move something that looked, after it was reduced and then reoxidized, it looked like we were getting something smaller. And in fact, when we looked at that microscopy-wise, we were seeing the following. So here we go. So here are some cobalt particles on the support. And when you oxidize them, what you start to see are these, we call them little domes, holy domes, in the sense that there's little holes in the middle. And it has to do with the fact that the reduced cobalt tends to move from the outside of the from the inside of the particle to the outside of the particle, and it does leave a sort of a void in there. So we kind of get these hollow donuts that form, and then when you go ahead, hollow domes, so when you go ahead and reduce them, they sort of crack because we have a hollow dome and it creates a lot of stress, boom, and the thing just reduces. They crack, and we see smaller particles surrounding this dome. But what you see here is that they're very close together. And here's another view. So that's exactly what we didn't want to get, right? Because now we have those graveyards that create, we don't like graveyards, and that's what we're trying to avoid. So you've made your own graveyards now. So you may think you did something really good because you got your catalyst, you got small particles, you run it for a short period of time, and you're back to where you were, but it doesn't stay there. It deactivates much faster. So that's not a good way to do reactivation of particle size. There are better ways. I'm not going to get into that today. What I'm going to go into next is just a little bit on issues in trying to design the catalyst. So knowing this, and knowing that you want to get nanoscale homogeneity, what can you do? Now, the answer is you can spend your whole life trying to figure this out, because it's a very subtle things, and it's very different on each type of support that you work on, and it can be very complicated. I'm going to show you a little bit of some of the issues. So, in designing the catalyst, you have a number of things that you have to deal with. The size of the cobalt crystallites, and we had that really nice work from Cryan and the group at Utrecht that is really nicely shown now that when you get below a critical size, 6 or 7 nanometers, you start getting impacts on your turnover number. And therefore, that may be the lower limit that you want to work with. You also have issues that the smaller ones tend to oxidize faster. So what is the right size? It's somewhere above what Cryan has shown us. Then you have promoters. You have the ability and the necessity to reduce the catalyst. And of course, besides the size, you have this uniformity. So you want to take all these into account. And this is data from a while ago that we have, just looking at some model systems back, this is a long time ago. Burt was even young when this was done. So here we have a plot of the cobalt time yield, that is the amount of CO converted per gram atom of cobalt as a function of the fractional dispersion. Shown on a variety of different supports, again showing that the turnover number is essentially independent of the support, especially if you stay, or exclusively if you stay above that limit where you start to get into impacts on the turnover frequency because they're too small. So that's one. The support can have a lot of influences, but it's not this necessarily, that's one. So with the promoter, there's all kinds of issues. One of them is you want to, normally the promoter is more expensive than cobalt, and cobalt itself is not dirt cheap. So you want to try to limit the amount of promoter that you have in there. It's normally a noble metal. The problem that you find is that as you cut back the promoter level, what you often see, just looking at data that you get, is the activity tends to be lower at sort of a lower or preferred promoter level than when you're at a higher promoter level. So how can you get to the same catalyst, how can you get to the same particle size, good distribution, and ability to reduce by still lowering your promoter size? So that's from a real world point of view, that's a parameter that you would like to play with as much as you can. But I will tell you that you also see that having the promoter there, large amounts of promoter, you normally will get smaller crystallites. That effect is something that I've thought about for many years. I don't really have a great explanation of why that happens, but it does. And so you face many obstacles in going down to low ones. It's a way of kind of stressing your system. Okay, so the role of the promoters lowers the reduction temperature, increases the dispersion, and so can often form bimetallics. And here's also another piece of data from when Burt was a kid. This was an XPS study of cobalt foil with surface ruthenium doping. And you can see actually the movement of the ruthenium. This is during reduced conditions where the ruthenium, the signal, ruthenium-cobalt signal would increase, and then on oxidation it would come down and come back up on reduction. And that, we believed, had to do with the rhenium tending to migrate to the surface during reduction. During oxidation, you could make mixed spinel phases that would have rhenium and cobalt in them. That would tend to mix things, and you would be able to see that motion. Okay, so you can get bimetallics, and you can, by forming it during this oxidation step and getting them mixed, you can wind up with better alloying in the resulting metal phase that you get during reduction. And having that alloy does reduce the temperature of reduction and does form smaller crystallites. So the promoters are a big part of this, and we don't totally understand everything they do, but they're very critical. Okay, preparing uniformly cobalt particles. This is a general slide on what do you do when you're working with supported metals to make them smaller. Well, there are kind of three ways that people make catalysts. One is a way where you have non-specific interactions. You don't do anything special. You just impregnate some solution onto the support, and you pray a lot. Well, that has a lot of problems to it. And largely because there are no specific interactions, so much depends on how you evaporate the water or the solvent that you use in making the catalyst. So you can get regions of supersaturation and then precipitation. It's a perfect method to get the gravy on. So instead, in many cases, people have tried to use directed either physical or chemical interactions. Electrostatic ones are a key one. And Professor Regalbuto has done a lot of work with that over the last number of years. This involves matching the charge on the particle, the precursor, with the support, using the concepts of isoelectric point and using strong electrostatic absorption. Another way is to use organics to form surface complexes. And that they generally then will increase the strength of the interaction between the impregnate and the support. It does come along though with having organics around. Sometimes that's okay, sometimes people don't like them. It's an extra cost. Sometimes it's a problem when you have to oxidize them, what to do with the off gases, exotherms, etc. So these are non-trivial issues, but they're very much into this world of Fischer Tropsch catalyst. So I'm going to show you a couple of examples of directed interactions, both with and without organic additions. So here's a nice one. Here was one where there was organics put on. It actually had a lower promoter level, and you can see it's a very nice distribution of the cobalt particles on here. So if you could do that, you can upscale it, you can live with the cost of the organic and all the issues of forming it. It's not a bad way of doing it. But in many cases, to the scale that a lot of these things are wanting to be used at, people would rather not use the organics. And so how can you now work with supports where if you're starting with, say, cobalt nitrate, how are you going to get a strong enough interaction so you don't wind up with a really ugly-looking beast? Okay, and so here's some data, and I'm showing Brian's data now of some nickel ones, and he actually showed that by varying the atmosphere, putting some NO in there, by calcining in NO, he could wind up with much nicer distributions of, in this case, nickel on a mesoporous silica than if he just did an impregnation and a calcination. So there's an example of one, and there were similar results that he had with cobalt, and the argument there was that it suggested the importance of surface hydroxy nitrates. So maybe that's a species that can interact strongly with the silica support. We saw something else, and this is kind of interesting. When we looked at the decomposition on our catalyst, and it's a complex catalyst, I can't tell you exactly what's in it, you can read the patents and sort of peruse what exactly it is. But when we looked at the decomposition of the cobalt nitrate very carefully, we saw that the nitrate decomposed in 2 steps. In fact, if you look at the DTA, that's the blue one here, there's 2 endotherms. They're separated. And if you look at the species, the nitrate-containing species that you might get, you would see over here, for this 30 NO and the NO2 type species, we also see 2 peaks. If you look at water, you only see it coming off, interestingly, during the first one. So that was kind of fascinating. And whenever we always see 2 things going on at once, we like to try to investigate further what's happening if we just go to the first one. And we found that could have a very large influence if you just stop this and actually give the catalyst some residence time after the first decomposition. It could be very different than if you just run through this very quickly, and like normally happens, and go through your formation of your catalyst. Okay, so this is just summarizing what I said. By the time you get through the second one, you're at CO304. And we think that there is actually a critical intermediate after this first decomposition step. I'll show you in just I have another slide or 2, I'll be done, what we think that intermediate might be, but it's something that's maybe interacting strongly with the support. It's not an organic, there's organic in here, but maybe there's something else. Okay, so here are some pictures of what we have at higher promoter level. That's kind of normal promoter levels. And here's different thermal treatments. If we do a direct heat up, this is the normal way, you get something that's fair. There are regions that are reasonable, like over here, the distribution. There are some where there's a lot of dense cobalt, and there are some here where it's sparse. If we do this treatment number 1, where we provide residence time after we go through that first decomposition of the nitrate, and we hold it there for some period of time, 10 or 15 minutes, and then go ahead and finish it, we get a different distribution, and it looks much more uniform. Okay, now if we really stress the system, and we go to lower promoter levels, we do the same treatment. It doesn't look as good, and that's normal. Normally when you get to lower promoters, you've got issues. But we did find yet another treatment, and this is a really strange one. You go through that first decomposition, you let it have some residence time there, and then you intentionally put it in a high water environment. So now you decompose, whatever that species was, now you're intentionally decomposing it. And now you go ahead and you continue the treatment up. Now you get something very nice, and the particles are actually as smaller than when you have the higher promoter level and with this nice distribution. Now, how to do this all in a scalable mode this is another situation, but it makes for nice experiments you can do in your lab. So what was that? What were we seeing? And the best evidence of what we saw, we actually assigned some peaks in the infrared that look like nitroceol, and they're in this region over here. So if we have our fresh catalyst, that's the bottom one here, we don't see it. The dry 120, we don't see it. It starts to show up at this first decomposition point, at its first intermediate hole temperature, at 160 degrees C. You can see this peak, which just maybe barely starting to show there, but it's actually not, and certainly not on the starting catalyst. That is a species that's there. When you go up and you expose this to water now, that is gone. It's totally gone. So it's a temporary, transient species that we think is reflecting what's creating a strong interaction with the support. So there's obviously a lot more to study here. Unfortunately, our project ended pretty much at this time. So I leave this for hopefully future work for someday. So quick summary, 3 intrinsic deactivation mechanisms, reversible, irreversible, mixed metal oxide and particle growth by coalescence, and really the theme that the metal scale homogeneity improves catalyst stability, and the details of the precursor support interaction are critical to get good dispersion, uniform distribution, and try to lower the promoter content. So I thank you. Let me just acknowledge my co-authors that were great to work with and that have helped us with a lot of the work. Some people that we work along with in the development labs. 2 of the consultants that we had during the course of this project. You'll notice Enrique, who we worked with a lot on this in the 1980s, had come back to help us with this. And finally, my thanks to both you and ExxonMobil for letting us talk about this. Thanks for your attention. I think I got time.
Thank you very much. We have maybe time for a couple of questions.
Yes, I have a question about the sintering mechanism.
Yeah.
So in your conclusion you said it's coalescent.
Yes.
But I would argue also from the data that you have, it's just the graveyard mechanism. So it just happens when they're already very close, and I wouldn't rule out oswald ripening based on this. I think it's just maybe occasional when they happen to be very close, but they don't move much. You also see
it's
actually
very
most of
hard.
them not
I
moving
agree
much.
with you. It's very hard to know exactly that's not going on. I mean, the only indirect evidence we have is that we never, and trust me, Chris looked at thousands, literally thousands of views of particles. We never saw a case where we had really small particles, which normally you'll get when you have the ripening. Some of the particles will transfer atoms and they'll become smaller. We never saw that, but when I talk to people like Avaya, he makes the same point you do, that even though you don't see that, it could really be happening. It's just that in some of the pictures we had, you can actually see them coming together. They kind of like find each other and wet each other. So I'm not discounting that. It could go on. And it's probably like everything else in this crazy world we live in. There's probably some mixture of everything. So yeah, I'm not that firm that I'll disregard that. Yes.
My question relates to the uniform distributions of the cobalt nanoparticles over your support. So what you show in the TEM is relatively high resolution images in the sense that you see 1, 2, 3 support particles, and there you consider the aggregation or uniform distribution. However, in many, many cases, if you go to lower resolutions, you observe areas of support where there's nothing and areas of support where possibly even very uniform distributions of the nanoparticles over your support. So my question is, what do you observe at lower resolutions in your system?
Well, it depends. So we very much what you're saying. Sometimes you see regions that are not wet. It's not a good thing because essentially what you're doing then is limiting your effective surface area that you started with. So that in general, for a given loading and a given size, will make the particles closer. And I know for sure that being closer is not good. You want to maximize that interparticle distance. So if the preparation is done very well, you'll limit that effect. I'm not going to say it doesn't happen, it does. Because obviously when you get into scale-ups and you start working with tons of material and not grams, all kinds of things happen. So yes, that is clearly you do see that.
Well, I think we need a couple minutes for the break, but Stu will be outside probably if there are more questions. So if you please help me again, thanks Stu for this great talk.
First met